what we're doing here is we're measuring the pressure on both the suction line and the discharge line. As we read here, suction and discharge, which are low and our high side. Okay. We're also going to, in this case, measure the temperature on the discharge line, because when you're using a TXV, it's important that it's charged per subcool, which is the difference in the temperature on the line versus the rated temperature for that pressure. Now, in this instance, our system tells us that this system should be reading a subcool of 10 degrees. Okay? Now, as we check our gauge here, which is reading 92, and the temperature on the probe for the meter, which is reading 82.6. So we're 9.4, which is perfectly fine. With the subcool rating, generally speaking, you can be plus or minus 3 degrees, and that would still be considered normal operation. In this case, we're off by 4/10 of a degree, so we're almost perfect, exactly where you want to be. So the pressures are good. The system's doing what it's supposed to do. The TXV is operating perfectly fine. We can tell by that temperature that it's doing what it's supposed to do, and that also tells us that there's no leak in the system, that the pressures have maintained from when it was installed to now. It's not losing any pressure. So we know everything's working like it's supposed to. Now, at this point, we've got that out of the way. We're done with the operating, or testing the amp draws while it's operating, so I'm going to go ahead and shut it down and do like I did inside, tighten down all the wiring connections, replace anything that might be burnt or damaged, and go through and make sure it's ready to run. And I'm going to turn it back on, and then we're going to go through the heat testing of the heat pump and make sure everything's doing what it's supposed to do and get you ready for that winter season. Okay, right now our voltage is off to the unit, so nothing's running. I'm going to go through right now. We're going to take this little guy out who made a wrong turn. I'm going to let him go back into the wild, and then we're going to go through the system here, the electrical system. Just like I did inside, we're going to make sure every wire is tight. Nothing is loose, any weak connections which could lead to a burnt wire or you know, a small repair that could just easily be avoided. Everything's tight here. Now, in this case, we have a heat pump which utilizes a defrost board, which controls the unit in switching from heating to cooling, and also switching into defrost mode on really cold days where the system might freeze up. It'll go into defrost. That's what this board controls. We're going to make sure everything on here is nice and tight and snug. Nothing's loose. It might cause a problem down the road. And then when we're done with all this, we're going to turn it on in heat mode, even though we don't need it right now. That'll give me a chance to test the defrost and make sure it goes into defrost like it's supposed to. A lot of times what we find is that a defrost board fails in the middle of winter. It may be a few weeks before one can come in because they're on back order. So we want to test it now, even though we're in fall and it's not cooled yet. You don't need it. If there is a problem, we want to get it replaced as soon as possible, rather than have that one cold night find out you don't have it. So, an example, a couple wires, and this is very common just from vibration from operation. Sometimes just from the factory, you have a couple wires that aren't on there perfectly tight. And while they haven't been a problem yet, we're going to go ahead and make sure they're pushed all the way into the spade, nice and snug, because that will eventually heat up with a loose connection from vibration, the voltage going through it, and melt. And if it melts one wire to another, we can have potentially major failure of components or parts and relays. So, also going to visually inspect our contactor, look for any burnt or pitting on the terminal. And it's 240 volts going through this, so you may have a little bit of pitting, a little bit of charring that will occur. But as long as the majority of the surface is smooth and flat and has a good connection, there shouldn't be any issues. And in this case, it's only a year old, so there really is nothing to report here. And now we're going to move on to the capacitor, which, like I said before, this is probably one of the most common repairs we have, specifically with the changing of the seasons, because the system has to run, goes from barely running in the early spring to running all day in the summer. One of the most common failures is this capacitor. Just that heavy workload of early summer. We'll change multiple capacitors a day because so many are failing at once. And like I said before, one of the main things is they become weak early, and if you don't catch it, that's when they'll end up failing. But if you catch them early, you can save a service call by replacing it while we're here for a maintenance. Okay, and the capacitor is reading perfectly like what we want it to see. Now, everything in here looks good. It's working good. Our amp draws tell us that the motor, the fan motor and compressor are working fine, and also that the capacitor and the relays are doing what they're supposed to. They're not causing any problems that would create an elevated amp draw. The only thing left to do now is we're going to go ahead and put it in heat mode and test the defrost board, make sure it's going to work properly when that time comes. And then also we're going to wash out this condenser coil, make sure it's got plenty of good airflow going through it, just to keep that efficiency up where it's supposed to be. Okay, so everything checks out good. 1-year-old system, operating perfectly fine, doing exactly what it's supposed to do. Only thing left to do now is to wash it out. Right now, I'm just putting it back together, and then I'm actually going to go inside and turn it off while I do this. What I'm using here to wash the condenser is a standard car wash soap and wax, and the reason we're using that is because it'll help keep the painted surface. It'll slow the rusting process, help keep that gloss coat on it so that it doesn't start to corrode away and rust prematurely. The most important part here that I'm concerned with is keeping the coil nice and clean, but also you want to keep the panels, you know, nice and clean as well with the soap and wax just to slow that rusting. Once that rusting starts, it'll eventually corrode and the cabinet will start to fall apart, and you'll end up replacing a system because the cabinet fell apart even though it was still running. I'll do my best not to splash it here. It's very common for houses around here to have dryer vents installed near the condenser, and all that lint from the dryer just gets sucked right up against the face of that coil, which causes it to run at a higher pressure, a higher temperature, and reduces the efficiency and the speed at which it can cool the house. By keeping this coil nice and clean, getting the maximum amount of airflow through there is what it's designed for. You keep the system cooling at its maximum efficiency and speed, but also it keeps the operating temperature down, which helps keep the compressor alive longer.